Okay, so what you've seen me do so far is repair bad workmanship that was done before. And then I did a lot more work I didn't show last night, which was to change some voltages inside to get these tubes running. Spent a lot of time on this. Today now, all hooked up and no sound, nothing, zero. Except, well, whatever you just heard there. Right? The only sound is this. So a real failure. So it's working as a percussion instrument right now. Anyway, so that's some kind of bad connection inside I have to figure out, right? Well, folks, that's it. After what I just showed you there, those random noises you were hearing, and noise when I was tapping on it, suddenly it started blowing fuses. It's continued to blow fuses. So it may be that this transformer is burnt out. That's very expensive to fix. Hello again, visitors and viewers. Okay, so if you've seen the first part of this video, it's turning the Marshall TSL100, breaking it down and turning it into a JCM800 project, and we're now firmly in that phase, having done the chassis work and circuit board layout, right? Okay, so this needs to be put on. The only thing holding me up from putting this on is that I want to do some heater wiring. The heater for the tube sockets could be done before putting this in. So we've done all the work on this circuit board here in the last video. And we have to do this side, which is the power supply side. So I've trimmed the board because I've measured how far it can go up to the power transformer. And I'm going to quickly lay the capacitors where they could go and mark and drill the holes and install turrets in those holes. A JCM800 or any of those older amps don't have the output transformer here where it sticks through the chassis. Usually it's right in the middle, completely outside the chassis. So this one has it sticking through a bit, and then you have this nice shield here, and I'm leaving all that in place. It kind of kills some of the room for the preamp, but I don't need to remove that. Okay, so I'll put my capacitors back on this board again, which has been trimmed. I'm crowding this. I don't want to waste space. These are right up against each other, and I've just left a little room for diodes and a couple extra little connectors there to do the standby switch. And choke. We will be putting a choke. Right, this is about the composition of the board here. I'm not going to really flare out these now. I want to paint this board. You know, the color difference between these two boards is a bit too glaring. These three ones here, these are for the preamp and phase inverter filter capacitors, right? Then there's going to be a bank of these four ones here. 4 diodes will go on these, in these spaces here, right? And at this point, the AC voltage from the power transformer secondary will come in on these two, because I think it's the diamond pattern bridge rectifier that I have to do. Right, so at the tip here, this will be where the two diodes come together. I'll send that out to this bank of capacitors, the first pair of capacitors, which is for the plate filtering. Then one from the same pair of turrets, I'll go out to the standby switch, right? I come back from the standby switch to here. And what will also be attached here, feed to the center tap of the output transformer, which powers the power tubes, right? And also we will have another wire go out to the choke. And then coming back from the choke, because the choke has just 2 wires, coming back from the choke will be here, and there will also lead to the second pair of filter capacitors, which again will be in series. Don't ignore the layout of how they are right now. So at that point, we have the power tube plates and screens both filtered coming off the rectifier, including the choke and the standby switch, right? If you can follow that with a schematic, you go ahead. I'm not sure, I don't even have any schematics printed out to do this thing. Cool, so that's it for now. I'm going to break this down and paint this. Okay, I have various wires to choose from. What we want to do is, we have a lot of current flowing through these bigger tube sockets, heater wires, because we're going to use EL34s, or who knows, maybe KT66. Basically, EL34s use 1.4 amps of current per tube. We hook them up not in series with each other, but they're parallel to each other in a sort of series way, going from one socket to the next, right? So the first set of wires coming in here, right, has to also bear the load of all of the other tubes' currents, collectively current. So basically, we need thicker wires here than here. For 12x7, there's 0.3 amps of current. Okay, so the wire load would be 0.3, 0.6, 0.9. I choose one thicker wire gauge here, and then I break down to a thinner one here. Okay, now Marshall uses a red and black wires. These are silicone jackets, which are not the best thing, not the best type of wire for staying in place. Like, you know, when high watts have those exact 90-degree bends and they sit right down on the chassis. These are not the best for that because they're kind of wobbly, right? But anyway, we'll try that just because Marshall has that color scheme. Now we put it in a drill, and there's just this nice way of using the drill to wrap the wires into a nice long spiral. You just zip on the drill's trigger and you got this nice spiral wrap, right? So I'm going to trim this and solder them onto those left side tube sockets. Okay, so here's the power section wired up. As I said, the silicone-based jacketing here is kind of rubbery, and it doesn't really so easily sit exactly where you want it, especially with this stranded wire, right? What's great about it, though, is that it takes a very high temperature before it starts to melt. So when you're doing your soldering, you don't have that risk of the insulation, you know, melting and peeling back while you're heating the joint, which happens so often with the regular PVC jacketing, right? So Teflon is the ultimate thing, which for not melting. That is pretty hard to strip. Right, so I'm going to do the same thing here. I'm not going to use the same wire. I'm going to move to a thinner one. Right, so this looks pretty nice going across. Okay, over at the drill press, this is the formal setup for the flaring of a turret board. I painted the one meant for these big capacitors, right? So there's two elements to this setup, really. We have a vise holding just this piece of steel that I've drilled a hole in. Now, the turrets have, you know, the taller vertical section where all the wiring goes, but there's always a flared base here, which is the widest part, right? So we're going to push the top down into this. So we want this whole size so that this could go in there easily, but the wide base is going to stay up at the top, right? So this is the part here sticking up that's going to go through the board, right? Now over the drill press, we're only really using the facility of the up and down press itself. We're going to put any kind of bit that has like a cone shaped tip, right? Like they have actual turret flares for this, which have a different shape, but I'm going to be, I don't have one, and you probably don't have one either, right? So this is a regular bolt tap, and it just happens to have this great flare at the other tip, right? So I'm going to put this into the chuck of the drill press, and I just kind of hand tighten that in there, and let me put that white as the background, and we set up the vise right below so that this tip is going straight into that hole there directly, and we'll clamp up the vise and table in place so that's not shifting around. Okay, so I just took some silver Sharpie and I just marked the back in the sort of mirror image of what I showed you before I painted the board. Arcing the back is easier in this instance, and all I need to do is put a turret into the hole, stick the board over the turret so it goes through. Now these turrets happen to be the same size as the holes in the board. I didn't need to actually drill them, and I'm just coming down on the drill press, and we just get a little bit of a flare out press, and that's it, right? So we got a flared turret properly installed. Actually, I need to be careful. I need to line up those grooves in the tops of the turrets. Okay, so in the space of a few minutes, we have that turret board. Anyway, so now I can quickly go and stuff this full of capacitor. Okay, so I'm well, about halfway along with this board. So I put the big ones in, started to put the small ones in. Now what I did was, electrolytic capacitors do need to be replaced at some point in time. It could be 20 years down the road, or you have some disaster and you have to replace a shorted one or something. But so basically what I did is I didn't leave the tips of these leads very long. I didn't want them to go all the way through and wrap around the back, right? I just wanted them to go in a bit so that if I wanted to replace them, I just need to do a basic reheating of the solder joint, right? And then let me just speak for a bit about the arrangement. These are pairs in series with each other, right? So basically this is the positive end. I need to attach this negative to this positive here. And then, so this is the negative end of this pair. It's a zigzag, right? Positive, negative, in between. I have to put 100K or 220K resistors across these terminals because that does a voltage divider, which makes sure that the voltage across each capacitor is evenly divided. For example, if we had 500 volts here and this is negative, we will put those resistors here. That would guarantee that this tip, or this part here, the middle, gets 250 volts. If you have 500 volts here, what's to determine how much voltage each capacitor experiences, if you understand what I mean, right? The resistance of the capacitor themselves may not be even internal. Right, so I'm doing that for both these pairs. But up here, these all would be the negative grounded terminals, and these would go to the respective high voltage spots. Okay, so here's the other side of those 100K voltage dividing resistors. So I have to kind of tack all everything in place even before starting with the actual wires that are going to be coming in and out of it. Okay, so now all of the parts for this board are fixed in place. I did this yellow wire going from here to here. Illustrates the series setup of those capacitors, as I've explained, and 100K is hiding down there, jumpering across each capacitor. Here, separate wires are going to go out to the preamp power supply, but their negatives get joined together. Okay, so the diode arrangement in a Marshall or any tube amp is directly related to what sort of secondary high voltage winding there is on the power transformer, right? There's three main setups that you would see in Marshalls and others, and I'm going to attempt to roughly describe them. And the reason I'm describing them instead of just sticking to the one that I'm working with is because as you study these old circuits, these Marshall circuits, you see these different types, and you need to determine how you're going to handle that secondary winding to get the voltages that we want. Right? They're all three different ones turn up in these Marshalls and Fenders and so on, right? So I'm going to roughly explain them. They have terms that overlap a bit here, but hang on, I'll try to clarify the terms in relation to the style of it, right? First one, full wave rectifier. Now, everything we're doing is full wave, but this one just tends to get called full wave. It's really full wave center tap. Okay? Right. So what we have here is the secondary coil, and this style I'm describing would have of the power transformer, and this one will have a center tap. And in this case, the center tap is grounded. Okay? So, how much voltage is there in between here and here? Let's use real simple numbers, right? To remember what's going on. Let's say there is, this is getting grounded, right? So let's say there is 100 volts between here and there, right? Total of 200 across the thing, right? The whole coil. When you go through a diode and you do rectification, the resulting voltage, subject to current draw and all of that, and method of filtering, 1.4, You multiply it by 1.414. That's a estimation of the rectified voltage, right? So what you'd get here, you join these two together through diodes. It's a symbol for a diode. It's a triangle with a little bar across the front. This would give you a voltage at the output here of 141.4 because we're multiplying 100 by this. On to the next one. We call this a bridge rectifier, but it really is full wave bridge. Now this does not have a center tap. So let's say this is a single winding, no center tap, and there's 100 volts across it, right? Now we'll put a different arrangement of diodes, okay? We'll put them in a diamond pattern. I guess this is where the bridge nickname comes from. And the back of that diamond gets grounded, right? So as this has a grounded center tap, this has a grounded back of the diodes. And the diodes will now point away from ground towards a positive end. They're all joined together, right? And again, you'll get the same thing, one, right? Yeah, full wave bridge. The third one I think causes the most confusion because it's basically this, identical to this, but it does have a center tap. It also has a center tap, right? And why do we have a center tap? So let's confuse everyone now. We got the center tap, but let's ignore it for now. Let's go back and set up the same bridge that we had for the one above, right? Same thing, all the diodes point away from ground. This is grounded again, like the one above. Everything's the same, except a center tap is present, right? Let's go again. Right, so we come here, and we'll have the same 141.4. But what's this doing? Okay, so I mentioned before that we have these two capacitors in series, right? And we have this set up here to even out the voltage distributed across them. So that same thing is done with this arrangement. What I did not draw into these is that all of these immediately after the rectifier, ignoring the standby switch and stuff. Normally standby switch will go somewhere here. But basically we have a capacitor. And this capacitor is one of these big electrolytics, or a set of electrolytics. And this will regulate the waves, because remember when we rectify, we are changing this into this, right? And the capacitor holds and releases charge, and if its capacitor is big enough, it will completely smooth the waveform and change this into straight DC current, right? So let's say we have an amp and we've got a pretty high voltage here, or whatever. I don't want the example here to conflict with the story I'm telling, but let's say we don't want one capacitor here, we want two capacitors, because our capacitors aren't rated as high as the actual voltage present, something like that, right? So we put two in a row, and they're grounded at the bottom. Now again, I talked to you before about getting the voltage evenly distributed across the capacitors, right? So how do we do that here? We could have those resistors like I mentioned, but this can also be used. This center tap can go right here in the middle, right? And this is now creating a division of 50 and 50 that is not grounded like that, but it is going to even out the voltage present across these capacitors. Now, when people see this on a Marshall schematic, they get confused and they go, well, which is it? Is it this one? I see a center tap. So is it this one? But I see a bridge. So they see this with the center tap and they go, oh, well, it's center tap. So they think it's this one, But then they see the bridge rectifier arrangement and they think it's this one, and it's just confusion. And it throws off people's calculations and estimations of what they might get out the front of it, right? So on this Marshall, the power transformer here happens to have this one, right? No center tap at all. So we'll be doing these, like join those together and join those together to form that bridge layout. Okay, so now our present phase is this here and this here. Soon time to arrange the board mounting. How we looking, folks? How we looking? Not bad, huh? We might pull this off yet. Okay, so we're on the laptop here, and I'm just going to show you examples from official Marshall schematics, the different versions of power transformer and rectifier that I was explaining before. So this first one here is a JCM800 from 1988, and this is the power transformer here. This is the high voltage winding. So we could see that this one has a center tap that gets grounded here come together to give us the positive voltage, right? So grounded center tap, this is like the first one we looked at, which we call the full wave, right? Center tap full wave, right? So the next one here, just gonna scroll through a few of them. This is a master volume model from the 70s. And down here we're looking at, this has the bridge. So this is like example number 3, because it has the bridge rectifier with the grounded back end here. But it has a center tap on the transformer that goes to the center of the filter capacitor stack, as I mentioned in our third example. This one here, we're down here, full wave, right? So this center tap gets grounded here, and it actually has its fuse, the high tension fuse, in line with it, which could be a little unusual. Sometimes that fuse is over in the high voltage section, but in this case it's in line with the center tap. Okay, next example. See, all these are all official Marshall documents, right? Okay, so this one is a 4 input 100 watt 1959, but it's from the JCM800 version, so made in 1988, right? Now this one's a little unusual. It has the power transformer here, and it's got the center tap, but it actually has a note saying center tap unused. Yellow center tap unused, right? And then this has the bridge rectifier and no center tap grounding or use at all. So this one is like our second example that I hand drew, where the bridge rectifier in the diamond shape, diamond arrangement of diodes, with the back end grounded, right? And effectively no center tap on the winding. The last one here is the schematic for this TSL100. This is the power transformer I'm working with. Now, again, all the other amps, the whole schematic was on one page, but on these is about at least half a dozen or more schematics to cover how complex that amp is. So this is the power transformer diagram here, and we could see this has no center tap at all. It's just the 2 lines. So when it comes up here, of course this has to be drawn more complicated than the others. Our diodes here, 1, 2, 3, 4, are actually in a diamond pattern, even though they did not draw it that way. And this has the capacitor stack, and it's got resistors across it to stabilize the voltage, rather than the other method where the center tap stabilizes the voltage. And so this one is like what you saw me do on the board, right? The 2 hidden resistors below the board, plate and screen capacitor stacks with those resistors, right? So the reason I'm showing you this is because if you're doing a sort of conversion project, right, you may have an old-time schematic that you want to follow, right, of some classic circuit or whatever you have in mind. but your amp that you're working with might have a power supply setup that doesn't match your intended project schematic, right? So you need to be flexible to adapt the power transformer in the project amp to the voltage requirements of the intended circuit of the project, right? So you need to know these different types of high voltage setups and rectification and filtering methods to go from your stock setup over to your intended project setup. Here's something that's been bothering me. If you look at this on this JCM2000, the back panel is so almost flush with the back of the cabinet. I'm pretty sure that that is less than a 1/4 inch, right? Less than a 1/4 inch, which means that all the parts before that were here, the jacks and fuse holders and everything, are in danger of getting bumped into when the amp is being transported, right? Like, look at this right now. I put some jacks here, put an impedance selector here, but if I put a knob here, that could get busted off. Look at that. That'll get busted off in transport. And then these fuse holders are gonna stick out a bit, and those could get just completely sheared off anytime I take this head anywhere and it gets bumped in the back. I have reordered the fuse holders which sit flatter onto the body here. I looked at the impedance selector options, and there were a few that were more flush mounted and flat, but they were going to conflict with this labeling that was here. So I figured I'm going to leave this. I'm not going to put a knob, but I'm going to cut this shaft short and saw a slot into it so it would be selected via a screwdriver or a coin or something rather than a knob. I'm not going to do the assembly of this amp as a one wire at a time, one solder joint at a time documentary. I'm not doing that. The video will get too long and it's just not that kind of tutorial. So I'm going to put this in, mount up the boards, start doing my wiring, and I'll give you updates here and there, but I'm not doing step by step. Okay? We've got to rush things along a bit. You probably agree. Okay, here we are now. Back inside. I finished up the heater wiring and put in this board. Now, because of the awkwardness of this double-decker chassis height here, I'm not really able to put bolts exactly where I want, right? So what I've done is I've drilled, instead of using the corner holes for the mounting bolts, I've drilled some other ones in areas where there was some clearance to put some mounting nuts, right? And I have put the board where I want it, and I have drilled through the board and then into the chassis below. Okay, so how we're going to be is we're lining up just about here. This one is going to sit right here, yeah? So they're going to be like that. And of course, I'm going to put the bolts through the chassis and arrange the nuts and so on so that they're elevated about 1 inch off of the floor. Okay? Now, I can't bolt that up now because I have so much wiring to do. I'm going to be lifting up the boards all the time. So I'm only really going to do that mounting at the end, or pretty much at the end. But for now, the style of wiring in this is that the wires go up from below the board into these turrets. So I'm going to have to be doing a lot of lifting and twisting. So what I'm going to do is just a few different categories, right? On the boards themselves, there's a number of connections that are within the board, like from one section of the board to the next. Especially things like the high voltage connections from here feeding into the circuit here, the high voltage parts, and then the grounds that are linked together, mostly on this side here. Same thing on the pots. There's numerous wires that are connected between the pots themselves, particularly to tone controls. And then there's a few long wires coming off the pots to meet the circuit board. Then you have the power tubes, which have resistors on them. So that could be a whole other session by itself. Putting resistors on the power tubes and then having long wires come off them, which will meet up with the circuit board here. So there's different sections that I can tackle. Another one that has to be done maybe later on is put some long wires going up into these turrets, which will later on be stretched down and put into the tube socket. And then at the end, start lacing it all together when I don't intend to lift the boards off to get underneath anymore. Here's what I did in this session. I put a ground bus wire across the back of all pots. Very hard to solder neatly on this because you really have to heat the heck out of it to get a blob going, and they don't look as neat as I would like them to be. Alright, so these wires are all the wires lacing the pots together, and these two blue ones are the ins and out of the tone circuit, basically into the treble control and out from the master volume. Underneath, I've put all the wires that are the sort of ins and outs of this board. There's one little thing I changed gears on. There was over here, I was fussing around before with some brown resistors, which were put here. And Marshall usually has a few of those resistors here. They're 10K voltage dropping resistors. I don't know, I just felt I could put those resistors right at the caps. There's two here and there's one hidden below here, right? And those resistors could do their job from this board, and I'm running the voltage out straight to where they need to go. They don't need to live over there. This blue one will go to the screens of the power tubes. There's a ground wire in the back here. A lot of these grounds are laced together, right? But I'm keep a separate ground for the main plate filter, right? Take note of that because that's part of the grounding scheme later, which is a whole other world on its own, right? AC wires going to the high voltage rectifier will come up here, right? And also we're doing a choke too, and the choke will junction to these terminals, right? So I bought two new fuse holders. Here's the new one. This is the one I bought before, and again, you see how much this one sticks out. It makes it liable to get busted off from moving the cabinet around. But this one here is much more flush, more in line with the depth of this. It's a better choice, but I have to tell you, in putting it in, it feels much more plasticish than the one on the left. This is a hard plastic with a metal nut. This one is, everything is plastic, right? It just seems closer to flimsy, like the original ones that I tore out in the first place. So I prefer the quality of this, but for dimensions, I have to go with this. Now, whichever side I wire up first, I'm less able to flip that side up to do any work on the opposite side. I have a feeling it's wiser to do this side first, so that in doing these, I am easier able to flip this side up to work under the right side. I'm starting off here. Okay, wish me luck. Let me tell you, this is stuff that gives a gray hair. I've done all of the wires to these ceramic sockets here on the preamp, right? And base almost everything on this side of the board. I also put from the phase inverter the lines that connect to the power tubes, right, which are here. They're kind of arranged funny, but this is nice and secure. But that's not how we usually see it. But the thing is that you have to float the resistors on the tube sockets themselves, so the junction is done off of the circuit board. Next session is this area here. Almost complete. This is actually preamp complete. Power tube sockets almost complete. Power supply almost complete. All we really need now is transformers in to finish things up. Okay, let me just look through and see if there's something I can point out. As I said before, if I ever need to take in building this board and assembling this board, I need to kind of get behind it to do the soldering, because the solder joints come up from below into these turrets. I don't really like this turret method. I think I would never move to this turret method from my eyelet method, which uses less solder, much quicker to do solder joints. This one, it takes so much heat to heat up the terminal that you really have to overheat the terminal to get solder to flow in the top and up from underside at the same time. It's an exercise in wasting heat and time and solder. Anyway, so that's my comment on turrets. They look cool, okay? Right, so if I need to service anything, or in the process of doing those joints, I cannot really have these wires very short. We do not have that kind of high watt method where the wires are individually as short as possible and making those neat straight runs and right angle turns and so on. There's quite a bit of slack on each of these, enough that I could lift up the board and work on the underside. The tone controls here, right? There's only one to the presence control, and there's one each treble middle bass. And then there's a couple for the master volume and preamp. Now, a couple little things, anything I can think of to point out. I put a shielded wire, something that's not always in the diagrams and pictures of these things, but there's a couple of long runs from the input jacks to the first two gain stages. And I've decided to shield those. So there's this black wire here. Right, so that first one goes from the input jack to the first gain stage. The second long shielded run is from the gain control, the output of the gain control, into the second gain stage, which is here. Now you will not, I put a little resistor here, same story. I put a little small 10K grid resistor right on the socket. Now you will not see that in a diagram. I've never seen that in a Marshall stock diagram or any photos, but this kind of thing, having a grid resistor right here on the second gain stage input, is something that you might see on a modified Marshall. You might see that on a high gain, you know, a Jose mod, or I don't mean, there's so many, I don't really want to name them. But when the gain really gets up there, it's, again, there's a little bit of noise and feedback suppression that could happen by having this. But I tried a 10K here. Let's see how that goes. That should help. Other than that, I've just kind of pushed the wires into a neat appearance for now. Over here, what intersects these two boards is there are several high voltage wires that go from these filter sections over to where those sections are being used, right? And like for this first one here, there's a hidden red wire underneath, and it comes up at these 100K resistors here. These are the first plate resistors for the first gain stages. The hidden red wire that comes out here, right on the second tube, there's a gain stage and a cathode follower. And the way that those two are wired together, there's this kind of complicated thing where we put the 100K resistor right on the socket itself. And there's another little jumper between plate and grid. And so this red wire here is feeding that from here. This one, third one here, comes up, hidden red wire again, comes up here, and these two resistors here, usually a pair of 100Ks, and Marshalls usually have 200Ks here, but in this case, for some reason, it does the same as the Fender having 100 and an 82. I'm going to have a little remark on that. I was working on some Fenders earlier on in the year, and I was noticing when I was doing my power test, there was an uneven wave on your oscilloscope. One, let's say the top half of the wave was taller than the bottom half, or the shape was different. Let's say the top half was sharper and the bottom half was fatter, something like that, right? It was an imbalance at the output of the amp, right? And I traced it backwards into the phase inverter circuit, and I realized then that one of these halves of the phase inverter were just putting out a taller, sharper wave than the other. And in that old amp, it was a early 70s deluxe reverb. So I replaced these two resistors in the Fender. It was 100K that had drifted out of spec and an 82K that had drifted out of spec. And when I replaced those two, out at the output, I had a fresh, very even output wave again, right? So it was here that had thrown the power output out of symmetry, right? So that explains why these two values are not exactly the same. It's a method of correcting a natural imbalance of the phase inverter design. Okay, so most of the innards are wired up. What is still outstanding is the power transformer wiring, output transformer wiring, and general grounding, which kind of encompasses everything. So right now I'm going to tackle power transformer wiring. This side here is the primary windings, and there's two different ways to wire this, depending on if you had 120 volt or 240 volt AC operation. And on the right side here are all of the secondary voltages, right? So I'm going to start now with the primary side, which is going to involve the power switch, these, and the IEC connector, and the mains power fuse. So what I've done here on these major connections of the mains, I've put some heat shrink on everything. Come out of the neutral, we go to the power switch. We come out of the live, we go through the mains fuse holder, and we continue on to the power switch, right? So this one, for the light to work on a Marshall switch, it's got to, it can't be a SPST switch. It's got to be a SPDT. Anyway, so from here we jump across to the primary windings of the power transformer. Now, if I make any major mess up in this project, it's going to be there, because this has 2 windings, and when they connected in series, you have 240 volts. Or if you connect them in parallel, you have 120. But you have to phase them properly. You can't mix up, you know, the ends of each winding have to be in a certain phase together. And if you get it the wrong way, you could be pulling too much current and blowing the fuse. Connect the blues together and the reds together. All that I marked myself earlier. Now, the next thing I'm doing is the secondary wiring. So far, I've just put on the heater lead. Now, I noticed that there is a set of 3 terminals for the heaters. This is what we call a center tap. In the original Marshall amp, I don't think it's used. It's not used, right? But it's sitting here unused, right? So what I could do is 2 ways to wire heaters. I can ground the center tap, which would lower the hum compared to how it is right now. Or I could put 200 ohm resistors from each of these legs to ground, which would make it quiet as well. Or you can have one of those hum balance pots. If you've ever seen a hum balance pot, that's what that is. It'll be like a 100 ohm pot where these are connected to the 2 outer edges of the pot, and the center is grounded. But for this one, I'm probably going to ground the center tap here. It's just the easiest thing to do, right? Now, the next thing, which is perplexing me, is these 3 wires. Now, this TSL originally had a whole bunch of solid state circuitry, and you need some low voltages to run those ICs and whatever, right? Millions of them. And then you also need about minus 50 volts to run the bias circuit. So what we have here is really a double winding, that is a center tap and 2 outer leads. This wire here leads to the original JCM800 style circuit, which is a single bias control. And I was going to put the wire, this would go to the bias adjustment pot wherever I end up locating it. Last of all, there are 2 little terminals here marked with red, and these 2 are going to the main rectifier diodes, which are this setup here, right? So basically, these 2 center turrets, these 2 here, this one and this one, will be receiving those wires from there. Okay, so another wiring session has gone by. The update of that is that I put in the output transformer, and I put all the wires going to the power tubes and impedance selector. Now, there were a whole bunch of these big wires that had clips from the original TSL, and I kept those wires. Right, so I ran those back. Those go to the impedance selector, and they jump across to the output jacks, and they also have a little line that goes, this is what we call the negative feedback resistor, right? Now, I'll talk about this for a second. Now, negative feedback, right, is a signal is taken, an AC signal is taken from the secondary of the power transformer, right? So it'll tap off one of these impedance taps, and they feed that back into the circuits in the area of the presence control and the phase inverter. That serves to quiet down and control certain aspects of the signal. Now, if you do not phase the connections of the transformer properly, you can end up having positive feedback instead of negative feedback, right? So if you switch on the amp for the first time and you hear a pile of squealing and you've been doing some output transformer work, then it could be you have the wrong phasing. It's a 50-50 chance to get it right, you know. So in that case, we would swap some of the leads. We'd swap the leads on the primary, like these 2 here. The ones labeled P, well, these 2. You'd swap those, and you would return the phasing to giving negative feedback. Right, so we move on. What I have done, I've installed a choke I just had a bunch of these laying around the workshop and I chose one. Marshall doesn't seem to have a specific value that they use on chokes over the years. Most seem to be about 4 to 5 Henrys, and some can be as high as 20 Henrys. So that's quite a wide scope, right? But that's in there. I've installed a negative. The bias pot is hiding under the preamp board here. I've decided to put it in a spot where it wouldn't accumulate any heat from the transformers or the power tubes, and it's sticking up on the top there, right? Out of the way of any prying, fiddling fingers. Power sockets have all been wired. You know, okay, so this does not look very neat, right? It doesn't look neat because as I said, I cannot bend perfect 90-degree joints on any of these wires. There's an awful lot of wiring hidden under these boards. Trust me, you don't want to see the wires that are under there. Of course, though, I've hidden a lot of wiring because usually on Marshalls, there's a whole bunch of wires crisscrossing across the top here. And I've hidden all of those below. So, of course, below looks a little messier than normal. What's left to be done is the grounding, the 2-star grounding scheme by which all of the preamp grounds are laced up together to one ground point, which should be bolted to the chassis in the vicinity of the power transformer. And then the high current grounds, which are the plate filter caps, rectifier negative, and power tube sockets would get joined together, and those would have their own grounding point as well. And then there's a separate grounding point for where the mains cable comes in, which is this green one here. So as much as you see these ground wires hanging around, right, I'm actually gonna boil them down to 3 ground points. Here is the next thing. We have a wiring almost done. We have to put in grounds, but there's another little thing we do nowadays when it comes to biasing tubes. We often, to make things easy, put a 1 ohm resistor between the cathode of the power tube and the actual ground connection. And when we are adjusting bias, we could measure the voltage drop across such a resistor, 1 ohm resistor, and the voltage drop across it would be proportional, directly proportional to the amount of current that's flowing through it, because it's 1 ohm. So if we read 50 millivolt drop across that resistor, means that 50 milliamps is flowing through it. So by monitoring the voltage drop on all of those resistors on each tube, we can see how much current each tube is pulling. And if they're equal, that's what we call matched tubes. And if they're all at the right level, that's what our whole biasing process is about, is to run the current pulled from each tube at a safe amount. We're looking for, in a case like this, we're going to be looking for somewhere between 30 and 40 millivolts per tube. That's a reasonable range of figures. Of course, the tubes won't be exact. One might be 32, one might be 35, but we try to adjust them within a certain range. It depends on the plate voltage and what type of tube it is, what type of wattage we're trying to get out of it. I'm giving you very rough estimates. I want to do on this amp, I want to make this an experimental amp where I could change power tubes and adjust the bias kind of quickly without having to take the chassis out of the cabinet, right? So I'm looking to put, a lot of modern amps have this. They have an external test point where you can poke your meter to a test point somewhere outside the amp and measure that voltage drop on those resistors inside. You don't have to open up the whole thing and stick your meter in here, right? Now, this amp actually had it stock. The stock setup on this amp had 2 bias pots and 3 little pins here. That is where you would measure the current pull from each bank of tubes. Of course, that's all been gutted out now. But it would be cool. I could drill 4 holes anywhere in the chassis or anywhere on the back and put test probes, test points like this. And these would be connected to those test resistors, right? 1 ohm resistors. But you know what? Why not put that test set right here where the original test and bias adjustments were, because it's quite close to the right place. Comes in here, and it's quite close to the right place where those resistors would be set up anyway. So I've cut this little piece of aluminum, and I'm going to be measuring and drilling 4 holes to hold these 4 test points to be mounted in that little oval spot I showed you. A hole every 3/8 of an inch, and I'm going to put it a 1/4 inch. The line will be a 1/4 inch from this edge. So well, I've scratched little marks onto the aluminum of where to drill. And the truth is, it's going to be very tight space. Okay, so I did this very quickly here at my drill press with just the simplest little vise and regular drill pieces, and that's not bad. That's it's not perfect. One is looking a little droopy, but it's going to do the job nicely. I still have to mark and drill the mounting bolt holes for this. Okay, so that is our little bias probe panel. So this is going to fit in there real nice from the outside, because that gives better clearance. And then we've got some bolt holes to put in. And on the inside here, it fits just right. So that's kind of the last piece in the puzzle I wanted to make before getting onto the grounding wiring. So that's the next session. Okay, I'm actually done wiring. I can put in a few tie wraps here and there to hold things steady in a few spots. But other than that, I'm kind of been just poking wires around in such a way that they look neat and kind of hide under the board and so on, right? And I did find a mistake. I had put some of these wires wrong. These are between the tube plates. Anyway, so what I've been doing, I'm just staring at this for ages to make sure I'm not making any mistakes. Start off with measuring the power supply, going down the line from one capacitor bank to the next, making sure that no funny resistances show up. Make sure that those are going to the right pins on the tubes, and then checking the same on the cathodes, the low voltage areas. And now after I film this, I'm just going to go through and double check this signal path. Very important, because when you fire it up for the first time, if any of the power supply sections are hooked up wrong, you're going to get blown fuses and maybe burning or damaging something. So it's just a very sensitive. Also, to my bias setup is a kind of guesstimate. If I have too high or too low of a bias voltage, I'm going to have to be changing some of these resistors here. I just kind of came up with some average values to start off with. I did the thing, I finished off the probe thing in the back here. Okay, and that's looking cool, I think. And I made a frightful mess with the resistors on the inside. I couldn't get any of these things to line up properly, but anyway, maybe I'll make it look a bit neater. So we'll be doing all biasing from the top back edge here. I left a couple of capacitors here hanging around it. These are longer than they should be, and there's 2 of them. One thing I would have talked about earlier is the brightening capacitors in these amps. They can be too bright, okay? And it's these values, this, and this, that determines that relative brightness. This is a 470 picofarad. Let's call it 500. 500, and there's 1,000 here, which may be too bright for me with the cabinets I'm using. So I put two 500s in parallel to make up the 1,000. If I think it's too bright, I'll take off one of these and reduce to a single 500. Okay, so I am satisfied with my double checking and triple checking all the wiring. I actually found a problem right here. On the first gain stage, I mixed up these 2 blue wires. One of the diagrams that I was following had the tube socket in a different clock to different angle from mine, and in reading it, I mixed them up, and I put them in such a way that we would have had like a non-stop constant feedback loop. Okay, so I am actually ready to brave firing this up. Do not consider anything I have here instructional. This is just my quick little test setup. I know what I'm doing. I don't have my current limiter in place. I'm just winging it right now. This is my DIY. This is not instructions for you. Okay, so we have my voltmeter hooked up here, and I flick on. I've already done this, but we can verify we're getting 500 volts on the dot at the rectifier, right? There are no tubes installed. I haven't even hit the standby switch. So what we see here is 500 volts coming out of the transformer, going into the rectifier, hitting the first two black capacitors there, getting rectified, and that's it. It's not even going to the choke or any of the rest of the circuit. That's just the immediate secondary wiring, and so far that's a success, which means I've hooked up correctly and interpreted correctly the primary wiring setup and the secondary high voltage setup. I'm now, okay, I checked my heater voltage right on the sockets of the power tubes, and I'm getting a high reading. I don't have it hooked up right now. The high reading is just under 7 volts. Now that's high because we're supposed to be getting 6.3, right? Now it's high because there's no tubes installed. And when the tubes are installed, the current draw will drag on the winding supplying that voltage, and it would go down. Okay, I would have expected to see about 6.5, 6.6. So to see 6.9 is a bit high, but there's 7 tubes to go in. Here, I'm getting only minus 18 volts on the bias feed to the power tube grid. I want about 40, minus 40 there, and I'm only getting minus 18. So I need to rework this circuit. I have to drop the value of this resistor. I may have to rewire the winding that is supplying the bias. There's no way I would put in power tubes right now. I have to get that bias circuit going right. Okay, so let me tell you what I think right now. The bias winding on this transformer was 3 braided wires, 2 white ones and a black one. There was a third mystery wire here, which I just blanked off, right? So I'm only getting minus 20 volts pretty much between the black wire and the white wire I'm using. Okay, so what I'm going to do is I'm going to dig this out. I'm going to measure the tip of this, and I think that I'm going to get another 20 volts off of this. So it may be it's a 40 volt winding that I have misinterpreted and hooked up as a 20 volt winding. Okay, after the initial test, I suddenly find I'm not getting any power. And look, this fuse holder is so shitty, this gray insert plastic type. Brand new. Brand new. So what? I have to stick something in here to make extra contact. It's not even putting enough tension to clip the fuse securely. You see the kind of shit we have to deal with in the amplifier building world or modifying world. Brand new parts that don't work, and a shit load of plastic. It'll never last. Okay, I just had to cut and insert a short spring from a guitar pickup height spring and push that into the inside of the fuse holder to get this to have an appropriate tension. And even then, it's not a perfect contact. So don't be surprised if I put these back to the old ones. Okay, just as I thought, there were 2 white wires and a black one. I grounded the black one to send one of the white ones to the bias line where that yellow clip is. I was wrong. That was putting out 20 volts. Now I've connected white to white, and when I switch on, I'm getting just over 40 volts. So I could work with this and put an appropriate bias voltage over this. So let's go ahead and finish this up. I'm trying to finish this up late at night, and my dog is annoyed with me because she wants to go to bed. Right, so I have corrected that problem. The 2 whites are the 40 volt winding, and I'm going to switch this on now and do a little prayer. Oh, it's on already. You know, praying is a good time to pray when you're working on high voltage tube amps. We're now getting 35. I think I could bump this up a little higher. Right. If I lower, I'm gonna have to lower this resistor here. Lower this resistor too. I'd like to go past 40 on this. So I'll swap a few resistors here tomorrow and I'll be closer to the target. Okay, so I've made a quick change. I've put 2 lower value resistors here. This was a 10K. I put a 470. This was 5.6K. I put a 470. And the idea is I want to get as much voltage as I can out of this. Now, fenders, all your classic fenders, usually only have one capacitor in the bias circuit. You would have this dropping resistor, the backwards diode, one filter cap, and then it would go to the bias adjustment. Marshall has always done a 2-stage, what we would call a pi filter, right? Capacitor, resistor, capacitor. And the idea is to get a bit smoother, more regulated of a bias voltage, but I don't think that it's really critical. It's something we could look at on your oscilloscope later. But this value of resistor is so low now that these are almost identical voltages coming out there. I will fire it up again, and hopefully this is over 40. That would be nice. Okay, so we switched on again here, and we are getting minus 54. That's fantastic. So this range is pretty good. Okay, now I'm going to switch on the B plus circuit for the first time, which is taking it off standby. And I have measuring one of the last voltages down the line there. I'll check everything, of course. I just want to make sure right now nothing blows up, right? If I shorted anything, I did anything backwards, we'll get an explosion, right? So down there near the phase inverter voltage, I'm getting offload, no tubes installed. First time this is switched on. Yeah, this should be pretty high. It should be up around 300. So any of those voltage banks I test along there will get a different result. And oh, it just keeps climbing. Because I guess maybe these caps are forming. It's the first time they're being used. Anyway, at least we have no smoke or blown fuses on initial startup. That's a great sign. And I'm just going to go through and start checking all the voltages, right? And they will all be higher than expected because there's no tubes installed. So there will be an initial testing, then we put the tubes in, then there'll be another testing which will show the real working voltages that the tubes will be living with. Okay, so we're fully fired up here. The standby switch is on, and I can go through all the way through all the different voltage points here and check that we are getting voltages that we should get all along the way. All these capacitors are getting proportionally the correct voltages, although they are all high. These are all higher than they should be. Actually, that's way too high. That's almost at the limit of the capacitor's rating. But these would come right down when tubes are in. So I'm keen to get tubes in here as quickly as possible, really. This preamp voltage is so high, right? This comes down. Oh, this is too high. Something's off. Anyway, we're gonna actually really have to see what's going on when the tubes are installed, right? But so far, no smoke, nothing's blowing up. For now, I'm just gonna put these lightly used tubes in and make up a quad set. I'm not really too partial about power tubes in Marshalls. To me, any EL34 sounds great. The Sovtex and Electro Harmonics, I have really loved those. I've tried Siemens, a couple of Mullards, JJs. I've used a lot of JJs. They all sound alright. Everything is sounding good. I might be having a little problem. I've just put these tubes in and I still find that the pins are a bit shaky, which I find very odd. Usually these pins feel much stiffer when a tube is inserted, right? So I'm not too happy about the way that these pins are wiggling around. We'll have to see if these sockets are any good. Listen, I'm no stranger to building amps. I've built about 40 amps completely from scratch. and probably the same amount or more of fender restorations. But I'm not really accustomed to digging around and rebuilding Marshalls, so you know, mistakes can be made. Okay, I have switched on. No sparks, no fires, no deaths yet, and we are getting a bit of bias coming up on one of the tubes. Lovely how this bias probe has come out, and it's going to be very convenient. So that's very quiet cold biasing. We're hooked up to a test load, so I'm going to switch over to the speaker, an actual speaker, so we're going to hear if some hiss and stuff is coming out. We can't just rely on the fixed resistive load, because a speaker will tell us if we've hooked up the output transformer plate connections wrong, which I've mentioned before. Positive feedback if they're set wrong. Okay, so if we hear loud squealing, we'll know that's wrong. I'm tuning up the volume knobs. I really don't hear anything, even though the tubes should be running. Let's get it a little more biased up and see what's going on. Okay, we've had dead silence in the preamp so far, and I think I see why. Look at that busted grounded wire down there. See that? That's why I don't like these solid core wires, boy. You twist them a few times and they break. So let me redo that ground there, and we should spring to life. The reason I picked up on that was because I checked the plate voltage of the preamp gain stages here. They were very high, 427. And when I checked the cathodes of those same gauge stages, it had the same 427, which means the cathodes were just up floating at the same plate voltage. They weren't being grounded. So that's how I spotted that broken ground there. So let's try it. Let's see what happens. Great news, our preamp has sprung to life. And as I turn the master volume, you can hear the hiss from the speaker come right up and tapping. We have a high volume coming there on the preamp, right? So let me get back to my voltage testing and biasing. Okay, everything is looking good. I'm getting appropriate voltage readings, like the preamp there. That's the phase inverter. I'm getting 280 on the plates there. I'm not sitting here with a voltage chart, because remember, I don't really know this power transformer well enough to tell you what all the voltages should be. Over the preamp, it's just a little bit lower, 263. This one is a little high. That's the one with the cold clipper 10K cathode. The cathode measurements seem appropriate. The main plate voltage, which we saw was a little hair over 500 earlier, is now settled to about 480. So that's a pretty healthy voltage for a 100-watt Marshall, and a little, just a smidge lower for the screens, right? And that's it, and we're getting sound. So right now it's working. Everything is working. Let me let's tune up, let's hear some hiss. Have some hiss, and let's see if the tone controls affect the hiss. Not much. The presence knob has a dramatic effect, but the tone controls don't seem to affect that hiss very much. Very mild. So far, tone controls don't seem so significant. Okay, I immediately discovered that problem. Mid controls, treble, middle, bass, the mid-range pot is usually grounded on its bottom lug. So this one here, this tab is supposed to be grounded, which it is clearly not. I put no connection on it, right? So let me put a little piece of wire from here and going down to meet this copper bus here, and our tone controls will work. All right, folks, problems. I have finally arrived at a point that I did not want to arrive at. Some of you more knowledgeable modern Marshall experts may know what was going to happen here, and I've been praying against it, is that I believe we may have a bad power transformer. Why I'm thinking that, of course, you saw me turn it on, check voltages, hearing sound and everything, but after about 15 minutes, the fuse blew, right? And I popped another one in, and I started to measure a lower voltage coming off of the high rectifier. It was dipping down to 470, which is no big thing. But I started to hear like a crusty, crumbly noise coming from the power switch, almost like it was pulling a lot of current, and I wanted to catch on fire. It was making a funny burning noise, right? So I've shut down and I've put on my current limiter light bulb device. It's down underneath the workbench. You're not going to see it actually. And I am now going to fire it up again and start analyzing the high voltage setup. If one of these is dead, an infant death of one of these capacitors, I'll be real happy, because I could swap that out for an even better one. I've checked the diodes to see if anything is shorted. They test fine on the meter. The good thing is that I'm having this problem even when the standby is switched off. This is off. So it's only the immediate secondary circuit that's from the high voltage winding to the rectifier and this first bank of capacitors. These are the only parts that are involved in the circuit that's now giving some kind of problem, right? So is it the case that this power transformer has an internal short and it's only showing up when the core wire gets to a certain temperature? That may be the case, because when I think back to when I was first analyzing this amp in its full TSL form, that was one of the things that was happening. For a while it was turning on, and there was noise coming out of it, but I never got any signal, and then it just started blowing fuses after a while, and then you had the big burn in the board and wacky bias and so on. So I'm starting to think, with all the problems, that burnt board, if you don't want to refer back to the first video, is this board. This is a cleaned up version of it, with this had a couple of meltdowns over the years, right? So I'm gonna do a series of startups now and see what happens. I've even gone as far as to wonder if I could swap in another power transformer, right? Ironically, that's from a Mesa Boogie. I'm praying that one of these is bad. Folks, that's it. We have bad news. This is a big crib death fail, infant mortality, and a further fail on the part of Marshall's TSL transformer. Okay, so I just swapped these in, because remember I was swapped these in a whole different set of plate filter caps, fired it up, blew a 4 amp fuse, no tubes installed. Now I just completely disconnected the high voltage leads, so the high voltage lines are just sitting there. They're not connected to anything. There's no part that could be bad that would cause this extra current to pull. And it instantly blew a fuse again, right? So we failed. This is dead on the high voltage line. The problem is, the question is, why did it work for 15 minutes in our last session? Why did it come on at all? We've got perfect voltages all down the amp for a while. We had it on, it was making sound. What was it that suddenly caused this to go? And I guess that short in the windings was lurking there all the time since it first blew up, right? Maybe a little bit of heat from me turning it on just kind of reactivated the short, right? So that's it. I have no way forward to go, right, except to swap out transformers. I don't want to spend $200 on a replacement for this. Why? For it to go bad again? So I have some scrap ones here. This is from a Mesa Boogie. This is from a dead Mark IV, right? The problem is the footprint for this is wider both ways than this. It doesn't fit exact. And truth be told, I wanted to keep this Mesa and the corresponding output transformer for some other sort of salvage project. This is a total orphan power transformer here. So this is a candidate. It's I'm not sure if it's really 100 watt capacity. It's just an old scrap transformer. I don't have details on it, but it sure is big. This may be what we turn to finish up this project, because that is shorted out and dead.